Good afternoon. Welcome to another video by Structural Analysis Made Fun and Easy. This is another video on the series on working out deflections from first principles. So today, I've got simply supported single span beam with a single point load, mid span point load. Today is actually the 28th of October 2021. I do the usual splurge at the end, then I'll get straight into the video for those people that are just here for the analysis. This is determine the deflection of a single span simply supported beam under a single point load at the mid span. So basically I've just drawn it out, figure 1. I'm just doing the reactions as well so that people can see where I'm working from. So let's just do this. Okay, so here you go. This is simply supported beam, single point load in the middle, the red arrow. There's this pin support here, pin support at the pin support at the left hand side. I'm calling that A. Pin support at the right hand side, and I'm calling that C. Sorry, that should be C. So I'm going to call this one, this position here is position A, this one, this middle where the load is, that's going to be called position B, and this load, this position at the right hand support, I'm going to call C, so that's A, B, C. So the distance, the span of the beam is L. The line down the centre is just to show that where the centre of the load, and that's at L/2. So basically what we had to do first is, if I just skip forward to show you why I'm doing this, so what we need to do is find out what the moment is along the length of the beam. This thick orange line, that is where it's L/2, and the moment is from, if I just borrow this one, what happens is you get, as we go from, we start at position A, and then we move along, we start at position A and then we move along from left to right. So the moment is clockwise, and it's moving from the support to the middle of the beam. So as you can see here, the moment is equal to the reaction times X. So I could just put that on there as well, just so you can see what I'm talking about exactly. That's going to be X. This is A. The midspan. The midspan of the beam is going to be, B, and that distance is going to be X. That distance, we're going to call it X as it moves away from left to right. The moment's given by M equals to, it's this reaction, but that's why we need to find out this reaction. Moment equals RA times X. Can I just write that on there as well without cooking it up? Right, yeah. M equals reaction vertical A times X. Okay, which is the distance along. So that means this only applies up until we get to the middle point where X is equal to less than L over 2, but we don't need to go any further. We don't need to go any further to the right. So basically that means we need to find RA. I know this is easy, so easy. I'm just working through it to show anyone who's just starting out. Maybe you're just starting your theory of structures courses at university. So what you do here, step 1 is, as many times as you've gone over it, is static equilibrium. We've got 3 equations we can use to find support reactions for any structure, even a simple beam. So this one, we've got 3 equations of equilibrium. That is vertical, everything applying to the beam. Vertically, mass equals 0, everything applied to the beam. Horizontally, mass equals 0. And then if we take moments about, for a pin supported beam, if we take moments, we can take moments about any point in the structure, and it should be 0, because it's just like doing a free body diagram. So basically, so on this beam, we got summation of vertical loads, RAV, which is the green one, plus RCV, blue one, minus P downwards is 0. So the sign conventions are, if I just, up, let's just make it easy. Up in the y-axis, up is vertical, and up is positive, downwards is negative. In the x is the horizontal axis. So from left to right, 0. From left to right, that's positive. And for moments about, let's say, the z-axis, so the z is firing you out of the page, anti-clockwise is positive, and clockwise is negative. So summation V, RAV plus RCV minus P equals 0. Rearrange RAV plus RCV equals P. So that makes sense, doesn't it? Everything that's going up is going to equal everything that's coming down. In this case, we've only got 1 point load. So let's call that equation 1. RAV plus RCV equals P. Summation horizontal. We have got pin support. Sometimes this is drawn with a roller support on C, but to be honest, doesn't make any difference, because RAH plus RCH equals 0, or if it was a pin support, RAH equals 0. Let's call that equation 2. So just to save time, we know that RAH plus RCH equals 0, RCH equals 0, RAH equals 0. And then finally, we just take in moments about A. So minus P times L over 2, so that's a clockwise moment, plus RCV times L, so that's the anti-clockwise moment. So basically, point load here, that's times L over 2 is equal to RCV times L. And if we rearrange that, that means that PL over 2 equals L times RCV. Let's solve that equation. RCV equals PL divided by 2 times L equals P over 2. So there we got it. The vertical reaction is RCV equals P over 2. So we could take moments about C and we get the same result, because beam is symmetrical about a middle vertical line. So put this back into equation 1. RAV plus RCV equals P. RAV plus P over 2 equals P. RAV equals P minus P over 2 equals P over 2. So both vertical reactions are P over 2. You could also do this, but you can check this by, say, taking moments about B, because then the positive RAV times L over 2 is equal to negative RCV times L over 2. So you can take moments about B to check this is correct if you're not sure. In terms of this beam, no horizontal loads. It's because there's no external forces acting, and there's no because it's a flat member as well, there's no horizontal forces generated. So so now we can go back to the diagram that I was talking about earlier. Now we know that RAV equal to P over 2. That means that M equals RVA times X, and RVA equals P over 2. Therefore, M equals minus PX over 2. As we move along the X, then that is getting bigger. That's also positive clockwise. As we looked at in the previous videos, we also know that M is equal to minus EI d2y over dx2. I've called that equation 11, and then so in this case, if we equation 10 was M equals to minus px over 2. So then if we equate equation 10 to equation 11, because they're both equal to M, then that EI d2y over dx squared equals px over 2, and then both the minus signs are removed. Okay, so that's the first bit sorted. That's just setting up the so we found the force reaction. This video is really for beginners because most people already know the reactions from the for a simply supported beam. Everyone knows it off by heart, basically. I hope you enjoyed this video. If you did, I'm going to finish this off in video 2. If you enjoyed this video, please like, subscribe to the channel. This for more BEng Honours, MEng, MSc, HNC, HND, Civil Engineering Theory of Structures. This video for. Please donate if possible. But if you enjoyed the video, please like, and see you in part 2.